Next is integral factor 1 over s. All the discussions which we gave for s apply here. The only difference is that here you are going to subtract because it is 1 over s. Again, as before, in gain it is 20 log g of 1 over j omega. Now this is like 20 log 1 over j omega. It is 20 log 1 minus 20 log omega. Recollect the properties of logarithm which we discussed in the earlier slide. Log of a minus b, a over b is log a minus log b. So we have 20 log 1 is 0. So 0 minus 20 log omega will be minus 20 log omega. So this is on y-axis, minus 20 log omega. On x-axis we have log omega as usual. So now the slope is minus 20. Now here is the interesting part. Now the slope is minus 20. If you compare this with for the case g of s equal to s, we said the slope is 20 plus 20 plus 20 decibel. But now we are discussing 1 over s, so it is minus 20 decibel. That means if you increase the frequency by 10 times to 10 times, the gain will decrease by 20 decibel. And if you increase omega by 2 times, that is octave, the gain will decrease again by 6 decibels. Now coming to the phase plot, the phase will be minus 90 degree. That means whatever we did for g of s equal to s will be reversed here. So now g of s is 1 over s. You can see the line is coming down, means it is a negative slope, minus 6 minus 20. Now the phase is minus 90. The next case is when g of s is 1 over s power n. Same discussions as we did for s square or s power n apply here, but in the reverse way. Mean the slope will be reduced by 20 times n, minus 20 n, and phase will be minus 20 times n. So this is an example for 1 over s square. The previous slides we saw an example for s square. Now this is for 1 over s square. If you compare this with that slide, the only thing that is different is the slope. It was positive there, now it is negative. It was plus 180 there, it is minus 180 here. So this slide shows the comparison of Bode plot for S and 1 over S. If you see this is for S, these two slides are for S, these two graphs, and these two are for 1 over S. If you see these two, it is just like a reverse. Here it is increasing by plus 20 dB per decade. Here it is decreasing by 20 dB per decade. Here it was plus 90, here it is minus 90. So that means if you remember for one of the transfer functions, that is if you remember the shape for s, g of s equal to s, these two if you remember, then these two can be just drawn from here, just reversing the signs. The next case is when g of s equal to s plus a. This is the Bode plot. Here if you see, now this x-axis is not in radians per second as it is, but multiplied by a. So that means it is not 0.01 radians per second, it is 0.01 times a rad per second. So again in the y-axis you don't have just magnitude, but you have 20 log a, 20 log a, 20 log a, it's there. Mean you are adding with 6, 12, 18, 24, 30, 36, 42. For this case, the Bode plot is up to A frequency, there is no change in gain, it is same level, and then it increases. But when it increases with the slope of 20 dB per decade, as we did before. That is to say, if I take A, and at A the frequency is 20 log A, then if I increase this to 10 times, that is 10A, then this value here, if we compare these two, here it is 20 log A, and here it is just above 18, so that is 20 log A plus 20. This is what we mean by 20 dB per decade increase. It was 20 log A here, 20, I mean at this point it is 20 plus 20 log A. This is about the gain plot. This point is where the gain plot changes from a constant value to a rising trend, and this frequency is called cutoff frequency. That is to say, if you have a function g of s is s plus 5, for example, then that 5 rate per second is called cutoff frequency. This is for the phase. Again, the phase doesn't change up to the cutoff frequency, up to point, up to point not cut 0.01a, and then from there it increases at a rate of 45 degree per decade. That means here it is 0.1a, multiply by 10, you have 1a, that is here. So from here to here, this increase is 45. That's the meaning of uh, this trend. Let us see this in action. So we have a function, I have taken a function called s plus 5, g of s equal to s plus 5. Now for this, I have got my Bode plot from MATLAB. This is the Bode plot. Here you can see, since we are using s plus 5, this is 10 power 0, that is 1 radians per second. This is 1, this is 2, this is 3, this is 4, and this is 5. This is 5. So at 5 till 5 radians per second, the gain plot is flat, and then it starts increasing. So this frequency is what we call cutoff frequency. Now for this case, what will be the starting point of this curve? We said before, if you see the last slide, it is 20 log A. The curve will start at 20 log A. That means in our case, it is 20 log 5. So this is s plus A. That means A is equal to 5. So 20 log 5 is 13.979. It's almost 14. So this is the reason why this dB is 14. That means it starts with 14 and up to this 5 radians per second it is a flat, and then it starts increasing at a rate of 20. Same thing goes for the phase. Okay, it goes at 45 degree. It is 0.1 and this is 1. From here to here you can see the change is 45. Now we go to 1 over s plus a. So let me directly go to the illustration. Previous case was s plus 5. Now I have 1 over s plus 5. As we discussed before, it is just a reversal of what we had before. There the slope was increasing, now it is decreasing. The slope was increasing, now it is reducing. Yeah, this is how they are different. Next we come to stability margins. What's the meaning of this margin? This margin says, for example, let us take a boundary within which you are allowed to go, and if you go out of the boundary it is a danger. That means this is the maximum space which you can utilize. Now if you say, okay, I will be here, that means what? That means you still have this much space to move around. That means you have this much margin before you reach danger. So instead of being here, if I say I'm going to move up to this point, that means your margin is reduced. Now you have only this much margin. Means you are going towards danger. Now how does it apply to our case? Suppose we have a system, and that system we want to make sure that it is stable. By stability margins, what we mean is we can find how much is the gain and phase you can still move before the system attains instability. That means how much more gain or phase you can add before you reach instability. We can take a correlation from root locus. In root locus we said that there is a particular value of gain which will make the system unstable. Now that is the value of k which will make you unstable. Now if you want to know where you are, how safe you are, how much is your safety, then these stability margins will help you find it. There are two margins which we are discussing. One is called gain margin and another is called phase margin. Now, gain margin is the factor by which the gain can be raised before instability results. We know this. If we keep increasing the gain, at one point the system will become unstable. Now, by how much time you can increase this gain before you get instability, that is called gain margin. This is found by finding the gain where the phase is minus 180 degree. We will explain what this means later. If this gain margin is below, if the gain is below 0 dB, then gain margin is positive, and it is negative if otherwise. Now phase margin is the amount by which the phase of the transfer function exceeds minus 180 degree where the magnitude is 0 dB. If you want to have a stable system, both gain margin and phase margin should be positive. Okay, let us see what this means. So this is what we mean by positive gain margin and negative gain margin. First of all, to find the gain margin, you have to start from the phase plot. You have to start from here to go to find the gain margin. Okay, so now let's assume this is the phase plot in the Bode diagram. Here is the place this is the place where the Bode curve, the plot crosses minus 180 line. Here is where it is crossing. Now from this point go straight till you reach the gain curve. See where you are reaching. Here you are now. At this point, what is the gain? The gain is below 0 because 0 dB gain is here and your gain is here. Since you are below 0, the gain margin is positive, which indicates a stable system. Now, conversely, in this diagram, again, this is the place where the phase curve cuts the 180 degree line. This is the place where it cuts. Go straight, and here is the place where you meet the phase curve, the gain curve. Since you are meeting the gain curve above 0, because 0 is here, so this place is above 0. So this means you have a negative gain margin, which indicates an unstable system. This gain margin and phase margin, both of them can be finite, both of them can be infinite, one of them can be finite. There are different scenarios possible. For example, this Bode diagram shows this type of a plot for gain and phase. Now let us see what happens to the gain margin and phase margin. To find the gain margin, start from the point where the phase curve intersects 180 degree. Now this is the place 180 degree. So this is the place where the phase curve intersects this 180 minus 180 line. Now from this point go straight up till you meet the gain curve. Here you are meeting the gain curve. Now at this means you are the point where this gain curve is met with this here, the gain is below 0 decibel because 0 decibel is here, so you are below 0 decibel. That means the gain margin is positive. Now come to the phase margin. To find the phase margin, start from the gain curve and see where the gain curve crosses 0 dB. So this is the gain curve. If you see the gain curve, it starts here with 0 but it does not cross 0. Mean nowhere this gain curve crosses 0. If the gain curve nowhere crosses 0 decibel, then the phase margin is infinite. So I want to reiterate this point. To find the gain margin, you start from the phase diagram and go up. To find the phase margin, you start from the gain diagram and come down. The next case is where the gain margin is infinite. Okay. Now for this case, to find the gain margin, as usual, see where the phase curve crosses 180 minus 180. Now the phase curve we see this area, this area here, this is the place where minus 180 is, but this phase curve does not cross this minus 180. It is going to touch that minus 180 asymptotically, but it's not crossing anywhere. Since the phase curve does not cross minus 180 anywhere, then we say that gain margin is infinite. Okay, then what about phase margin? To find the phase margin, start from the gain curve. Here is 0. So this gain curve crosses this 0 decibel line here. And from here come down here, you are meeting here. That means you have a very small, this is the place where you are going to meet. So this gap from where you met this line, this curve and the minus 180, this is a very small margin. So we can say that the phase margin is very small, which indicates a probable danger, means the system may go to instability. Now this is the case where we have both are finite. That means, before I go further, let me make one thing clear again. To find a system is stable or not, we have to find two margins, gain margin and phase margin. Both of them should be positive if the system has to be stable. Now, how to find the positive gain margin? Start from the phase diagram. See where the phase curve crosses 180 minus 180 line. From there you go up till you meet the gain curve. The point of meeting the gain curve, if it is below 0 decibel, it is a positive gain margin. And to find the phase margin, you will start from the gain curve. You will see first where the gain curve crosses 0 dB line. From that point you come straight and you meet the phase curve. The point of meeting the phase curve, if it is above minus 180, then it is a positive phase margin. Again the system will be stable. If these things are happening in the reverse form, then the system will be unstable. Now let us take this Bode diagram and see what is the case. Let me start with finding gain margin. That means I will start from the phase curve. So phase curve is here. I will see where the phase curve crosses 180. Here is the place, but again here is the place, but this phase curve does not cross 180. Maybe it will touch asymptotically, but now it is not crossing. So that means the gain margin is infinite. Now come to the phase margin. Phase margin, to find the phase margin, you will start from the gain diagram and see where the gain curve crosses 0. The gain curve does not cross the 0. It not even touches this. So that means that phase margin is infinite. So in this case, both of them are infinite. Gain crossover frequency means it is the frequency at which the gain curve crosses 0 dB, and phase crossover frequency means is the frequency at which the phase curve crosses minus 180 degrees. Now let us take another example of a Bode plot and see what the case is. This Bode plot is for this transfer function 25 over s square plus 4s plus 25. Okay, let us start to find gain margin. That means we have to start from the phase curve where the phase curve crosses minus 180. Now this is 150. Here is 150. Here is minus 200. So here somewhere roughly here will be minus 180. Let me now straight this and see where this minus 180 touches this here. That means from this point I will go straight up till I meet the gain curve. So here is the point I meet the gain curve. At this point, decibel will be about minus 30 roughly. Now is it positive or negative? Since the point of meeting this gain curve is minus 30 is below 0 decibel. So this is a positive gain margin, and the gain margin is roughly 30 decibels. This is about gain margin. Now coming to phase margin, we will start from here. We will see where the gain line crosses 0 dB line. This is 0 dB. And here is the point where the gain curve crosses 0 dB line. This is 0 dB line. Now from here you drop vertically down till you meet the phase curve. Here is the point where you are meeting. And now the phase at this is roughly minus 125 degree. Since this minus 125 is greater than minus 180 in terms of value, this is also a positive margin. That is, here is minus 125 and here is minus 180. So the phase margin is also positive because this line meets the phase curve above minus 180. So this is also positive margin, but how much it is? It is minus 135, sorry, minus 125 minus of minus 180. So this will be 55 degree is the phase margin, and it is positive. Let us see the use of a Bode plot for an example 4, which was done in part 7a. So this example we already solved by hand calculations in part 7a. This is the screenshot of this problem. So the question said, if you have a function input 4 sine 2t and is the transfer function given to you, what will be the response or what is the output? We did the calculations by hand and we found that the gain was 0.1545 and the phase was minus 0.9685 radians, and these things we did by hand. Now we will check these numbers using Bode plot. This is the code I used to get this Bode plot. We will discuss how to get a Bode plot from MATLAB later, but for the moment just look at the output. So here this is the phase plot and this is the gain plot. This problem says the frequency is 2 radians per second. So what I do, from in this Bode plot, I go to 2 radians per second. Where is 2 radians per second? This is 10 power minus 1, that is 0.1. This is 10 power 0. So this 10 power 0 is 1. This is 1 radians per second. So that means this is 2 radians per second, this place. So for 2 radians per second, if I go straight, in fact I got the data from MATLAB itself. We can see here it says frequency is 2.02 because I could not place the cursor exactly at 2 radians per second, so it shows me 2.02. At 2.02 seconds, the phase is minus 55.9. It is in degrees. Okay, and the gain is, or the magnitude is minus 16.2 decibels. You have to be extremely careful with the units here. Okay, this minus 16.2 decibel is the gain at this frequency. Now let us go to the hand calculations. What we did, we found what? We found the gain is 0.1545. It is absolute number but not decibel. So what we do, we will check whether minus 16.2 in decibel is same as 0.1545. So let me go to MATLAB. Point 1545, 20 log 10, 0.1545 is minus 16.2214. That's what MATLAB shows here. Minus 16.2 is the gain. Now minus 55.9 is the phase in degrees. What we got from hand calculation is in radians. So let us check this also. 55.9 minus, we have for 180 degree, 55, 55.9 over 180 minus is minus 0.9756. This is in radians now. This is the same as what we got by hand calculations. Okay. Now the reason I show you this is, you should not think part 7a is something different from part 7b. In part 7a, what all we did, we are doing it here also, but using a Bode plot. In fact, what you can practice is, you can take the same transfer function, apply some other frequency, and find the gain and phase by hand calculations. Now that you have a Bode plot already with you, you can check that answer with this Bode plot. Let's see another example, example 3. The question says, obtain the phase and gain margins of the system for two cases where k equal to 10 and k equal to 100. We have a system like this in a unity feedback, k over s, s plus 1, s plus 5. Now what we are supposed to do is, for the k, when k is 10, what is the gain margin, phase margin, and when k is equal to 100, what is the case? So this is what we are about to find. Now this is the solution, again got from MATLAB. This is the case. These two diagrams pertain to case where k equal to 10, and here these two are for k equal to 100. Now what is to be seen here is, when k equal to 10, let us see the gain margin. We will start with where the phase curve crosses minus 180. So this is the place, and then we'll go up straight. We are meeting this line below 0 because 0 decibel is here. So we are meeting it somewhere below 0. So we have a positive gain margin, and that gain margin is 8 dB plus. Now coming to phase margin, we start where the gain curve crosses 0 decibel line, that is here. You come straight, you meet this phase curve here. Now that means you are meeting the phase curve above minus 180. So this gap roughly is 21 degree. Since you are meeting it above the minus 180 point, the phase margin is also positive. So when the gain k equal to 10, we got both the margins positive, means the system is stable. Now let us see what happens when the gain is increased to 100. Again, these are the two graphs for gain and phase. Let us find the gain margin first. Now this is the place where the minus 180 line is crossed by this phase curve. So from here I'll go up straight. I am meeting this line, the gain line, above 0 because 0 is closed here itself. 0 is here, but that means I have crossed 0 and I am here now. That means 0 is already crossed, means I have already crossed the safety limit, and this difference between this point and 0 is 12 dB, but it is minus now because I am meeting the line above 0. Now coming to the phase margin, see where this curve crosses 0 line here. Now from there you drop down, you meet this curve here. That means you meet this curve after 180, below 180, because 180 is over here itself. So you are crossing 180, means since you already crossed 180, minus 180, you have a negative phase margin, and that is this 30 degree. Why 30 degree? Because this is 1 minus 210 degree. So this difference is 30. Now since both margins are negative here, the system is unstable. This is the use of Bode plot. This tells us clearly what happens when the k value, the gain, is changed. Now let us see how to use MATLAB to get the Bode plot. There are different commands available depending on what exactly we want to do. If you want to get the Bode plot, just a plot, then the command is simple. It's called Bode bracket systems, which is the system we are going to define. If you want to get the gain and phase at a given omega. That means I know one particular omega value, and at that omega value I want to find the gain and phase. Then you will use this command gain phase left hand side arguments equals Bode cis omega. The command log space can be used to limit the frequency range for the plot. This means, for example, in this graph, the frequency goes from 0.2 to 10 rad per second. Now I can, if I want to change this range, then I can use the log space command. If you want to know all the margins, gain margin, phase margin, then the command all margin can be used. Okay. So what we do now, we had finished example 2 just now. So example 2 was this. This is example 2. What we will do is, for this example, we will find the phase and gain. Remember, here I am not going to find the phase margin and gain margin. That is not my purpose. I want to know just the phase and gain at a given frequency. That is, for this frequency, it was 2 radians per second. You can go back here. This is 2 rad per second. So for that frequency, only that frequency, I am going to see what is the phase and gain. So this is the code I am going to use. This is the place where I define my transfer function S3 over S plus 3, S plus 5. Now I am fixing my omega because I want the gain and phase only for this frequency. Now after fixing this frequency, I give this command gain comma phase equals Bode within brackets cis comma omega. Means now I am specifying that I want this phase and gain only for that radians per second, that is 2 rad per second, and this is the output I got. Again, you can compare this gain and phase with what we got before. Gain was 0.1545 and phase was minus 0.96185 radians. Now let us see what is the number we are getting here. 0.1545 exactly. Remember that when you give this command, the number you are going to get for gain is in absolute numbers. It is not in decibels. And the phase you are going to get is in degrees, minus 55.49. I showed you before how this degrees corresponds to this radians. So by this, what we have done now is we have proved that the value of gain and phase, what we got for the transfer function by hand, is the same as what we get from the Bode plot. This is an exercise which we can do. Here there's a system given to you, and the question says, using the ideas of part 7a, should be part 7a, find the gain and phase at a frequency of 10 rad per second. So for this system, you will find the gain and phase using the ideas developed in part 7a at this frequency, and then check your answer with Bode plot obtained using MATLAB. Find the stability margins for this system.